So, how can we use the wrapper? Like you see that here this core 1, core 2, so they are connected, they are there in the system. So, here it is put as P1500 wrapper. Actually, this this P should not be there now, because when this was originally proposed to IEEE, so that was the when it is proposed that this P suffix P prefix remains. Okay. So, once it is accepted, then this P goes. Now, this 1500 is an accepted standard. So, this P should not be there, but anyway in this slide it has come in. So, you just keep in mind that P is no more required, but for new proposals this P is required. So, what we have is this user defined parallel TAM may be designed from source to sink, and through this WPI and WPO lines. So, they will be fed to this core individual core wrappers, and that will finally go to the core. So, the individual cores, they get input from these functional inputs, they get input from this WSI line, and also parallelly from this WPI lines. So, based on that, whatever input points that this core has so they will be getting the inputs, and their responses can be given to functional output, or it can be for normal operation. So, it will go to functional output. For test operation, it will either go to WSO or it will go to the WPO, this parallel output. So, that way this WPI WPO lines, so they may be configuring the whole thing. So, I can have a number of cores, and there are WIR wrapper instruction register, and this wrapper instruction wrapper port. So, that will be controlling all these points. So, this test access controller, this JTAG tap controller, that is this is at the system level. So, we have got this JTAG tap controller, which is 1149.1. So, it has got TDI, TDO, and this test mode select, test clock, and T reset. So, they are coming to this JTAG. So, this makes the serial TAM. Okay. So, this is a 1 bit serial TAM that is made here, and the response is coming back to this JTAG controller. So, this is a serial TAM, 1 bit TAM, and here I have got the parallel TAM. So, you can take help of both the TAMs for transporting these test patterns to the cores and getting the responses from the cores. Okay. So, but most of the cases we will see that it will be using this parallel TAM for transporting the test pattern and responses rather than this, but this will be used more for configuration purpose. This serial part WSI, WSO, this serial part, serial TAM. So, this will mostly be used for configuring the WIR register or this bypass register, things like that. So, we have got this is a typical example of say RAM wrapped embedded code. So, this is a core. So, suppose it has got, it is a core A, we call it. So, it has got a number of functional inputs D0 to 4. It has got three functional outputs Q0 to 2, and there are 2 scan chains, scan chain 0 and scan chain 1. Scan chain 0 has 6 flip flops, scan chain 1 has 8 flip flops, and they are coming from this. So, naturally there should be 2 scan input and 2 scan output. So, SI01 and SO01. So, these are the two scan in and scan out lines, and then so there should be control like scan clock and the normal clock. So, they should be there. Now, you see that this one, so this core, when we are putting it into a wrapper, okay. So, when we are putting it into a wrapper, so it may look something like this. So, you see here, so this D0 to D4, so they were the functional input. So, they are going to this wrapper cells, buffer boundary cells, and then they may be connected to the D0 line. This buffer cell, so it also gets input from many other places. So, it may get, so there so through this WSI line, so it is going to this buffer cell, and it can say the first cell, say D4. So, it can get input from this WSI, and it can get input from this WPI. Okay. So, it may be parallelly loaded, it may be serially loaded. So, whatever mode it is selected, so based on that it will either be loaded serially from here, or it will be loaded parallelly from here. So, this particular buffer cell, boundary cell, so it has got a functional input, and 2 test input, one from serial interface, one from parallel interface. So this depending upon this instruction that we have here, so this multiplexer and this cell will be programmed so that the appropriate input comes to D4. Similarly, all these are put onto a chain. So we don't have, so similarly this D3, it does not get any it does not get any parallel input. So it has got one functional input and one serial input through this line. So this is there are only 2 inputs, so there is no choice. Similarly for D2, so it is again put onto there is a choice here, so it can get input from this scan cell, this boundary cell, or it can get input from this parallel input, or it can get input from this functional input. So D2 is a combination of 3 points, 3 input points, and that will go to D2. So you see that this WPI lines, so WPI lines can be used to feed these data inputs. Then this so since I have got say 6 input points, so all these WPIs cannot be used to feed them. Okay. So even if you are doing a parallel loading, so the first the second the cell D3 does not get a WPI. So if you are trying to load D3 parallelly, so still it will see a scan, it will see a delay of 2 cycles. First cycle it will be loaded here, second cycle it will be loaded here. So based on the WPI lines, so I may have to make a choice. I may have to make a choice like the cells onto which we are going to connect it. So here these two boundary cells, so they are put on say one WPI 0, the next 2 are put on WPI 1, and the third one is there, so it is put on WPI 2. So that way if we are trying to load these registers, this WPI this wrapper scan cells with this particular with values from WPI. So at least, so I will require 2 cycles. So in one cycle the value will come to the first cell, second cycle it will go there. So similarly parallelly in the first cycle, so this cell and this cell may be loaded, and in the second cycle, so this cell and this cell will get the value. So that way it requires 2 cycles for loading the pattern, even if I am going by a parallel loading of patterns. And serial loading, so everything is a chain, so I have to go by all the 5 cycles. Then comes the point of this one, this scan chain loading. So scan chain loading, it's you see that I can load the scan chain serially. So this is put onto a serial one, or I can load it from this parallel point. So this WPI 1, so it may be loaded by this, and this scan cell, so it can be loaded by WPI 0, and it can also be loaded from this point. So this is basically this scan cell can be output of this scan cell is connected to the input of this scan cell. So if we choose that particular mode, that means these 2 scan chains are combined into a single scan chain of 14 flip flops. So that is one type of design. Of course, by programming these multiplexers, so we can keep this scan chain lengths to 6, 8 or 14 based on our choice. Similarly, this Q output that we have, so Q output can directly go to the chip outputs like here, this Q0, Q1, Q2, or it can be put through this multiplexer. So it can be put into this, say this line. So it is going to through this multiplexer, so it is going to WPO line. So there are three WPO lines, WPO 0, 1 and 2. So they are actually so the last one we are taking directly. So this output is fed to this, and the second output is fed here. So that way this WP, it can be put onto this TAM lines, okay, or it can be taken out via this WSO. So this this particular multiplexer, so it is getting input from this chain of the cell boundary cells, or it is getting input from this bypass cell. So based on that, so it will come here, and finally this multiplexer, so it will select whether it is selecting the instruction register or it is selecting the data. So this select WIR, so based on the value of this, so it will either pass this WIR value or it will pass the content of whatever is coming through this line, a bypass or this boundary scan register, so boundary scan cell. So, that way you see this wrapper design can be done. So, by programming these multiplexers properly, so we can have different types of configurations now. So, that we will see slowly. So, in normal mode of operation, what is going to happen? So, this D0 will come to D0, D1 will come to. So, these are the functional inputs that we have seen, and in the wrapper these functional inputs are coming and they are transferred to the functional inputs of the cores. Similarly, here these responses Q0, Q1, Q2, so they are transferred to the wrapper outputs Q0, Q1 and Q2. So, that is the normal mode of operation. In the serial bypass mode, so rest of the thing is not connected, because this WIR will select this bypass. So, this is not there. So, this bypass will get selected. So, whatever WSI is coming, so it will be bypassed like this, it will go to WSO. So, this is the bypass, serial bypass mode of operation. Then serial internal test. So, in serial internal test, so I have to apply the test pattern. So, what is happening? So, you see that it is serial. So, serial means I have to pass the test pattern serially through this scan chain. So, it is through this line. So, it comes through this chain, it reaches this scan chain, then you see that pattern shifts through this scan chain and reaches the scan chain 0. It shifts through scan chain 1 and reaches scan chain 0, and then scan chain 0's result, 0's output is actually connected on connected to this chain of this Q0, Q1, Q2. So, what is happening is that, so this is serial internal test. So, the first the test pattern will be shifted like this, then the response will be captured onto this scan chains and these flip flops, these boundary scan cells, and then they will be transferred through this WSO line to the output. So, this is the serial internal test mode that can be implemented. Then we have got the serial external test mode. In serial external test mode, so this D0, D1, D2, so through this functional patterns will be applied. Then this WSO, so this is the serial input is applied through this, and through this WSO line, so we can load this pattern here, and then this through this the pattern may be loaded through this WSO line. So, it is loaded. So, now you see this scans, this chains. So, these flip flops that we have, so they are actually transferring the pattern coming from here or coming from this WSI. So, based on the pattern that we need to transfer, so it will be going there. So, now it is the scan chains are not affected. So, it comes to this point. You see, so this is external testing. So, what is required is that it is for the interconnect testing. So, say this output from here, so it is going to be connected to another core's input. The interconnect between, say, core A is connected to core B. So, this part is actually the core B's point. First, through this shifting pattern, through this the WSI line, we will be shifting in the pattern that we want to apply here for doing the serial test, okay, for doing that interconnect testing. So, that way this pattern gets loaded onto these output cells, and then as soon as this has been loaded onto the value, so values will be available at core B's D0, D1. So, these inputs, so they will be loaded here, and now that will be scanned out from the core B's chain actually. So, then the values will be available at WSO of core B. So, we can see whether the values that we have put at Q0, Q1, Q2 of core A got loaded into this D0, D1, D2, those lines of core B. Okay. So, that is why this connection is shown, both the lines are, both the connections are there, but for the core A, if it is a core A to core B connection, this WSI line will first load this Q0, Q1, Q2 these cells, then in core B it will be checking, it will be loading these values D0, D1, D2 etc., the functional input values onto the corresponding scan cells, and then it will be shifted out at core B. So, at core B WSO we see whether it has been tested properly or not. So, that is why it is called X test mode. Or if it is, if there is some user defined logic that we need to check. So, the user defined logic can be given value through this Q0, Q1, Q2, and the responses may be collected from this UDL into this D0, D1, D2 of the next core. So, that can be done. Then we have got parallel internal test mode. So, parallel internal test mode means these values will be loaded parallelly from the this parallel interface. So, the serial interface does not do any work. So, this you see that there are 3 input lines. So, the 3 WPI lines 0, 1 and 2. So, this is loaded. So, this first line will be feeding this one. So, it will be loaded here. Then it is this line itself will be used to parallelly load all these flip flops. So, it will be loading these 5 flip flops. Then this line WPI 1 will be feeding this scan chain, and WPI 2 will be feeding this scan chain, because that is the best way to do the balancing, because this has got 6 flip flops, this has got 8 flip flops, and here we have got 5 flip flops. So, they can that is the most balanced distribution. So, of this 5, 6 and 8 length, as if there are 3 scan chains now, one of 5, one of 6, another of 8 flip flops. So, they are fed by 3 different WPI lines. Similarly, at the WPO side, so these primary outputs from the core, so they are forming a chain. So, that is one line. Now, this scan chain 1, so that is forming another line, and this scan chain 0, that is forming another line. So, WPO 0, 1 and 2, so they are actually taken, these scan outputs are taken, and they are forming the parallel output. So, in the parallel internal test mode, so we are applying the test pattern parallelly to this primary inputs and the scan inputs of core A. So, core A evaluates the input, and the results are available in the scan chain as well as this Q0, Q1, Q2. So, they are scanned out through this WPO lines. Okay. So, that is the parallel internal test mode. Similarly, the parallel external test mode. So, here the operation will be similar, but now this so this D0, D1, D2, so they will be loaded parallelly. So, first I need to load the values in Q0, Q1, Q2. So, that will be done by means of so this Q0, Q1, Q2. So, that will be done by means of where is it, this Q0. So, this is basically this one. So, Q0 is loaded serially. So, from D0 it is loaded here, and from D1, so the values that are coming, so they are loaded, and in fact this WPI is 0. So, that is actually forming this chain. So, loading these patterns. Okay. So, loading this pattern. So, it is otherwise similar as that serial input, but excepting the thing is that now it is loaded parallelly to the WPI interface, but it is testing the interconnect between core A and core B. So, if we come to this test wrapper optimization part, then this may be a typical situation like a core. It has got 2 scan chains in it, one consisting of 4 flip flops, another consisting of 8 flip flops, and then there are 2 inputs and 2 outputs. So, one possible wrapper design may be that so if I have got only 2 lines, so wrapper so this number of TAM wires given to me is only 2. Now, what I can do, I can put these flip flops onto a one chain, on this primary input, primary outputs onto one chain like this, and then these scan chains, they may be combined, and we can do a connection like this. So, this way what happens is that I have got 4 flip flops in one chain and 12 flip flops in another chain. So, that is a highly unbalanced design. Now, when we are doing testing, so for every pattern, you see I have to load all these flip flops. Now, number of cycles the shifting that will be needed for loading this pattern is any test pattern is now 12. So, if we do it in an unbalanced fashion, it is like this. Other option, maybe I have got only 2 lines, but what I do, I connect these 2 inputs, then this flip flop 4 scan flip flops and these 2 outputs onto one chain. So, I get one chain of length 8 here, and another chain only the scan chain. So, that is also of length 8. So, here the maximum scan chain length is 8 for loading a test pattern. So, it will be requiring a shifting of 8 cycles. So, that way it is a balanced wrapper design. So, number of shifting needed per test pattern will be 8 compared to the case that previously in this case. So, it was 12. So, now we can understand that this test application time will be dependent on this wrapper design. So, basically this distribution of this primary input, primary output and these scan cells into different chains. So, that makes it that has got a definite impact on the test time. So, so this is one way. So, the objective of this optimization procedure is to minimize the length of longest wrapper scan in out chain. So, so basically that is the objective. So, we want to minimize the longest wrapper scan chain. So, that has to be done. Another objective may be to minimize the wrapper scan chains that are created. So, you see that in one suppose I have got 4 chains. So, in one scan chain there are 32 flip flop, other scan chains they have got 8 flip flop. So, what I do, since this has got 32 flip flops, so I cannot connect anything else to it. So, what I do, so there are more inputs and outputs, there are 4 inputs and 2 outputs. So, I just try to do the best one that I can do. So, I put 2 here, 1 here and then 2 here, 1 here, 1 here, and this has got only 1 there. So, I do not connect between the scan chain, I just attach the primary input and primary outputs to this wrapper. So, now the tam width is equal to 4 because I have to feed 4 such channels. So, tam width is equal to 4, but shifting but for testing every pattern. So, every test pattern. So, I need to give 32 pulses. So, 32 shift pulses. So, 32 cycles will be needed to load the pattern. So, on the other hand, so I can do a bit more justice. So, if I can do it like this. So, instead of taking 4 lines, so the 4 lines are provided, but I do not use those 4 lines, I use only 2 lines. In one line I feed this scan chain with 32 flip flops. On the other line I have this 8 flip flops of 8 the chains of 8 flip flops, we can concatenate them. So, that gives me 24 flip flops, then 4 flip flops, 4 input flip flops at the end, 2 output flip flops at the other end. So, that makes it 24 plus 6, 30 flip flops. So, the chains are more or less balanced now and the number of scan chains are also less. So, there can be 2 objectives that we can have. One part, first part is the minimize the length of maximum case. So, in both the solutions the first priority is satisfied. So, the minimizing the length of this maximum chain. So, both the cases the answer is 32, but still we see that the second answer is better than the first one because it has reduced the number of tam lines that are needed. So, number of tam wires to be dedicated for this particular code. So, that will be less. So, that way we can have this wrapper design part done taking care of these 2 priorities. And in fact, so if we just plot this wrapper tam width and this longest wrapper scan chain. So, in general it is expected that if I allow more tam width, then it will this length of wrapper chain, the longest wrapper scan chain length will reduce. But in some cases it may not happen, and in fact this is the situation. So, as we are in, so this is for 1 tam width 1, only 1 bit is provided. So, everything, all the flip flops, all the scan chains, all the input output points, so they are put on a single chain. So, this is the length of the longest chain. Then there are 2 the number of tam lines provided is 2. So, in that case we see it is reduces slightly, 2, 3, 4, 5 also it reduces, but for 6 it up to 6 it reduces, but for 7 and 8 there is no reduction. So, it may be the case that at that point, so even if I go for this 7 and 8, so it is there is no this maximum chain length cannot be modified because the wrappers this scan chains may be such that it for these values it does not reduce. So, again after some time it reduces. So, 7, 8, 9 from 10 again it reduces. So, that way it gives some sort of staircase behavior. So, you get this type of staircase behavior. So, this particular observation has been taken into this design wrapper algorithm. So, this design wrapper algorithm, what it does is that it takes one scan chain and tries to attach more scan chains and this flip flops to it, so that this maximum length is reduced, maximum length of all scan chains is reduced, and it also reduces the number of scan chains. So, it uses some sort of best fit decreasing heuristic for the design of bin, and that way it works. So, this is the wrapper design algorithm that is followed. So, once this wrapper design has been done, so we can go for different types of TAMs. So, there can be different types of test access mechanism like multiplexed access. So, the TAM this is the TAM width at different time instants. So, this TAM is given to different codes. Okay. So, C1, C2, C3. So, they are given TAMs at different times and they are combined in this fashion, or it may be that it is daisy chained. So, this first TAM is given to core 1. So, if core 1 does not use it, then it will be it will be given to core 2. So, somehow this control signal has to be generated by this core 1. So, if it is not using the TAM, then it will be passing this TAM to the core 2, and then this it will be given to core 2. Some lines will be going there, and if it is not using the TAM, then it will tell that it is not using it. So, this TAM will be given to the core 2. So, this way we can have different types of TAM access mechanism. So, once we have done this wrapper design part, then we know that for every core what is the what is a good wrapper design, what is a good distribution of these wrapper scan cells, and once we have that, then we can go for generating this we can go into this test access mechanism design, and knowing that this will, if I give it this much of TAM width, it will require this much of test time. So, we can knowing the volume of testing for individual cores. So, we can figure out like which core test time we want to minimize maximally. Okay. So, if some core is taking lot of time, so we have to do something so that its test time is less, and for that purpose we need to have this scan chains, this wrapper design information available to us, and we may like to provide more TAM width to that core, so that this test time is less for that core. Okay. So, this way this this wrapper design can help in the TAM design process.